Look at this cyclist moving on a track, and you can see that first his velocity is increasing and then it stays constant, and a little while later it starts reducing again. So what we say is that whenever the velocity of an object increases or decreases, and that is what we saw in these time intervals, we say the body is accelerating, and when the velocity is constant, that happened here, we say the body is not accelerating or has zero acceleration. So the cyclist moved from 0 meters per second to 5 meters per second in 5 seconds, and then he continued cycling at a constant velocity of 5 meters per second for 15 seconds. And then he reduced his velocity from 5 to 0 meters per second in 10 seconds. So the formula we use to find average acceleration over a time period is given as A average is equal to V2 minus V1 by T2 minus T1, where V1 is velocity at time T1 and V2 is velocity at time T2. So looking at this equation, we can say that acceleration is nothing but the rate of change of velocity, because you have delta V in the numerator, and let's go ahead and write it as well, and delta T in the denominator, and you can see the units of acceleration will be meters per second square. In fact, if you rewrite meters per second square as meters per second, what we see is that it expresses the meaning of acceleration a lot better, because this actually shows by how many meters per second the velocity changes every second. Now let us calculate the acceleration in time interval t equal to 0 second to 5 second. So here average acceleration is v2 of 5 meters per second minus v1 of 0 meters per second by t2 at 5 seconds minus t1 at 0 seconds, which equals 1 meter per second square. And since it is positive, the direction of this acceleration is this. Then here the average acceleration is 5 meters per second minus 5 meters per second by 20 second minus 5 second, which equals 0 meters per second square, which is quite obvious, and we didn't really have to calculate because no velocity change means no acceleration. Then here the average acceleration is equal to v2 of 0 meters per second minus v1 of 5 meters per second by 30 second minus 20 second, which equals minus 0.5 meters per second square. And since it is negative, the direction of acceleration should be this. And in fact, this makes a lot of sense. That is the direction we've got, because if the cycle is slowing down, the acceleration has to be in a direction opposite the velocity to slow it down. So one other observation you should make is that even though this number is negative and the velocity is reducing, we still call it acceleration, or in other words, acceleration is a word to be used when dealing with changes in velocity, even if the velocity is reducing. And we'll talk more about this in a few minutes, where you'll understand why we still call it acceleration. Now, let us say the cyclist moved again from 0 velocity here to 10 meters per second in 5 seconds. Then we can say that the acceleration is 10 minus 0 by 35 seconds minus 30 seconds, which equals 2 meters per second square. So if you compare this acceleration with this one, what you can say is that the acceleration here is twice that over here, which means velocity change is twice faster than here. So here every second velocity is changing by 2 meters per second, and here every second the velocity is changing by 1 meter per second. So in this section, at end of 31 seconds, the velocity became 2 meters per second. Then at end of 32 seconds, it became 4 meters per second. At the end of 33 seconds, it became 6 meters per second. Then at the end of 34 seconds, it became 8 meters per second. And finally, at the end of 35 seconds, it became 10 meters per second. So you see how the magnitude of acceleration progressively increases the velocity, or in other cases, decreases the velocity. Now we will move on to the idea of instantaneous acceleration. Earlier we saw that this is the average acceleration between two times. Now, instantaneous acceleration is defined as a rate of change of velocity in a given instant or a given point of time, and is written as A is equal to dv by dt. So if you're given a velocity time graph, then the slope of the graph at any point of time would be the instantaneous acceleration at that time. Also recall that v is equal to dx by dt, so we can rewrite this equation as A is equal to d by dt of dx by dt, which equals d2x by dt2. So you could also define acceleration in mathematical terms as the second derivative of position of a particle with respect to time. Okay, let us use this as the definition of acceleration and look at a few velocity time graphs and tell if the instantaneous acceleration is increasing or decreasing. So in this one, we can say that the angle theta is increasing, and since slope at any point is tan theta, slope is increasing, therefore the acceleration is also increasing. In this graph, we can say theta is decreasing, and therefore acceleration is also decreasing. In this graph, your curve is actually a straight line, and so theta is constant, and therefore acceleration is also constant because tan of theta will give the same value at all points. Also, you can see acceleration is positive, but you can notice that the particle starts with negative initial velocity. In this graph, theta is again constant, and therefore acceleration is constant. Also, theta is less than 90 degrees, and therefore tan theta will be positive. You may also remember that the line is tilting up and right, so slope has to be positive. Therefore, acceleration is positive and velocity is increasing. In this graph, again theta is constant, therefore acceleration is also constant and positive. Also, the initial velocity is positive. Let's look at this graph, and what we see is you have a straight flat line and theta is equal to 0. Therefore, the slope tan theta is equal to 0 at all times, or acceleration is 0 at all times, which is also obvious because we can see velocity is constant. Okay, in this next graph, theta is constant, therefore acceleration is constant. But since theta is greater than 90 degrees, you get negative slope, and therefore acceleration is negative. Also, the initial velocity of the particle is positive. Okay, in this graph, theta is again constant, therefore acceleration is constant. But since theta is greater than 90 degrees, the acceleration is negative. Also, initial velocity is 0. So now we come to the part where students often get confused, and that is the direction of acceleration and the sign we need to use to indicate the direction of acceleration. So acceleration, like velocity, is a vector quantity, and therefore it should also have direction. So if the sign of acceleration is positive, it means it is acting in the positive x direction, and if the sign is negative, it is acting in the negative x direction. However, often students think that positive acceleration means velocity is increasing and negative acceleration means velocity is decreasing. This is incorrect, and you can pause the video and repeat the words, "This is incorrect." Well, This happens because in everyday conversation, we associate acceleration with increasing velocity or speed. But in physics, this is not the correct way of interpreting the sign. So always remember, the sign of acceleration indicates the direction of acceleration and not whether the object is increasing in velocity or decreasing. So let me give you an example where you will get more clarity on what I'm trying to say. So if a car is moving at a velocity of minus 25 meters per second, which means it is moving in the negative x direction, and it is brought to a stop in 5 seconds, then how we calculate acceleration is we say v final is equal to 0 meters per second minus v initial is equal to minus 25 meters per second divided by time, which is 5 seconds, and you find acceleration is 5 meters per second square. That is, it is positive. So you see, even though acceleration is positive, the velocity has reduced from 25 meters per second to 0 meters per second. So positive acceleration does not necessarily mean that the velocity is increasing. Rather, positive acceleration means that the direction of acceleration is in the plus x direction. Again, you can use common sense and visualize that if the direction of acceleration was in minus x direction, instead of this that has been calculated, the car would have never stopped. It would have kept moving and increasing in velocity. So the acceleration had to act in the opposite direction to reduce the velocity of the car, and that is exactly what happened here in our calculation. Another mistake students make is that they think that if the velocity is reducing from minus 25 meters per second to 0 meters per second, the velocity is actually increasing because 0 is greater than minus 25. But you need to remember that the minus sign indicates the direction only or the vector nature of the velocity, and the number 25 indicates the magnitude. So a velocity of minus 25 meters per second is greater than 0 meters per second. So you need to be very clear about this, and then remember that if the velocity of an object is reducing, the sign of acceleration will always be opposite the sign of velocity, and if the velocity of the object is increasing, the sign of acceleration will always be the same as the sign of velocity. Let me give you another example where a car is moving at a velocity of minus 10 meters per second and its velocity is increased to minus 20 meters per second in 5 seconds. The acceleration of this car will be v final, that is minus 20 meters per second, minus v initial, that is minus 10 meters per second, divided by time, which is 5 seconds, and this equals minus 2 meters per second square. So you see, the velocity here was increasing and in the negative x direction, so there had to be acceleration in this direction that enabled the increase in velocity, and therefore the acceleration that we calculated turned out to be in the same direction. Okay, let us take a situation where a car is moving at minus 20 meters per second, and then after 10 seconds, the velocity becomes plus 10 meters per second. So the acceleration here is v final, that is plus 10 meters per second, minus v initial of minus 20 meters per second divided by time, that is 10 seconds, and this equals 3 meters per second square. So let us summarize the situation. The car was moving in the negative x direction at minus 20 meters per second. The acceleration was acting in positive x direction, and the final velocity is plus 10 meters per second in positive x direction. So how we interpret this is that the car was moving in this direction, the acceleration started acting on it in this direction, and it brought it to a stop, and the same acceleration continued acting on the car and reversed the direction of motion of the car in positive x direction till its velocity became plus 10 meters per second. So let us now see how an acceleration versus time graph can be made using velocity time graph. And remember, we had made this velocity time graph using the position time graph in the earlier lesson. So let us now derive the acceleration time graph from this velocity time graph. So we saw earlier that in this part between t equal to 0 and 1 second, the object was stationary and had 0 velocity. Therefore, the acceleration here is 0. Now, between 1 and 3 seconds, the car's velocity increased, which means it accelerated. And how we can find the average acceleration is by using this formula, that is Vf of 4 meters per second minus Vi, that is 0 meters per second, divided by time, that is 2 seconds, and this equals plus 2 meters per second square. Also, you can get the same answer if you find the slope of this line, that is 4 meters per second minus 0 meters per second by 3 second minus 1 second, which equals plus 2 meters per second square. So we show this as a straight line here between 1 and 3 seconds. Now, between 3 and 8 seconds, we see the velocity is constant, hence no acceleration. So here we show acceleration as 0. Now, between 8 and 9 seconds, the velocity is reducing. Therefore, acceleration must be in the opposite direction and can be found as V final is equal to 0 meters per second minus V initial equal to 4 meters per second divided by t, that is 1 second, and this equals minus 4 meters per second square. Now let us attempt one final problem that will bring everything together. So what we have here is a particle whose position changes with time and is given by the following equation, that is x is equal to 4 minus 27t plus t cube, where x is in meter and t is in seconds. And the question is to find the velocity and acceleration of the particle. So we can say velocity would be v is equal to dx by dt, which equals minus 27 plus 3t square, and acceleration would be dv by dt, that is a is equal to 6t. The next question is there a time when velocity is equal to 0? So we put v equal to 0 here, that is minus 27 plus 3t square is equal to 0, and we find that t is equal to plus or minus 3 seconds. That is, the velocity is 0 at t equal to plus minus 3 seconds. And minus 3 seconds should not bother you because it essentially means that the velocity was 0 3 seconds before you actually started measuring. See, another way, it does not necessarily mean that the particle started its journey at t equal to 0 seconds only. It might have been moving earlier. It is just that you decided to start your experimentation at t equal to 0 seconds as the reference time. The next question is, describe the particle's motion for t greater than or equal to 0. So to describe the particle's motion, we basically need to examine its position, velocity, and acceleration at various times. So we see that at t equal to 0, the particle is at plus 4 meters and its velocity is minus 27 meters per second. That means it is moving in the negative x direction. The acceleration is 0, that we obtain by putting t equal to 0 here. T greater than 0 and less than 3 seconds, using this equation, we find that the particle continues to have negative velocity and continues to move in minus x direction. Using this equation, we find its acceleration is no longer 0, but is positive and increasing, because you can see that as you put various values of t between 0 and 3 seconds in this equation, acceleration will keep changing and will be positive. We also observe that the direction of velocity is negative, but the direction of acceleration is positive, which means the particle must be slowing down. And we actually found earlier that the velocity became 0 at t equal to 3 seconds. For t greater than 3 seconds, using this equation, we find the particle has positive velocity and increases with time and moves in plus x direction. Acceleration also continues to be positive because in this equation, any value of t will give you a positive acceleration, and this acceleration continues to increase in value. So if you want to understand this section better, you should go through this playlist, which can really give a lot of depth to how you understand this topic. Also, if you like this video, please give it a thumbs up and see you in the next video.